My name is Manar Mostafa, and today we're gonna talk about superconductivity. How does a magnet get the ability to fly? That's what we call superconductivity. Superconductivity is when the resistance in a solid totally disappears. This can happen under very low temperature, uh, generally below 20 Kelvin, but depend on the different type of materials. This temperature is called a critical temperature. Let us focus on this graph. This is a normal metal and superconductor. It's the relation between the resistance and temperature. So as we can see here, with decreasing temperature, both in superconductor and the normal metal, the resistance decrease. But they differ in this part, which is at very low temperature. In normal metal, we can see that with decreasing temperature, the resistance decrease with no error. But in superconductor, at a very specific point, which is the critical temperature, we can see that the resistance equals zero, totally vanish. At this point, which is the critical temperature, it gives the solid different properties, which is of superconductivity. It makes the solid more unique.
Why? 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 Why?
Before we say why this is happening, if we bring a wire, conducting wire, have a flow of electron and put it in a liquid helium, so temperature it reaches the critical temperature, so it will be converted to superconductive material. So the intensity of the flow of electron in this wire will not decrease among years. Let's come back to our conductor and observe just one electron and assume the conductor has been cooled down by helium, so the thermal vibration are negligible. As the electron is being pulled to the positive side of the battery, it flies in between atoms of the lattice. These atoms are positively charged because they have lost their electron to the conduction. This means that the electron will cause a slight attraction of the atom, since it's negatively charged and the atom are positively charged. If you have a positive atom clamped together in a local disturbance, they are a bit more positive. Now, a new electron flying in will be attracted to this local disturbance because it is a slightly more positively charged. You will probably expect, since like charges repel, these two negative electrons should repel each other, but they don't, because in reality many more atoms in the lattice are actually a part of this distribution, and the attraction happens over 100 to thousands of atoms. The attraction causes these two electrons to go together and bind to what is called copper pair. But this bond is extremely weak, and even thermal vibration will break it. That is why we need the liquid helium to decrease this vibration. When two electrons go into a copper pair, something interesting happens. Proton, neutrons, and electrons are usually what is called a fermion particle. There is another type of particle called the bosons. A photon is bosons. I'm not going into details about this, but being a fermion, like the electron means that no two particles can be in the same state. That's why we see atoms like this. We have fermions, electrons orbiting the nucleus if they were bosons instead. They could all go into the same state, so they will all clamp into the ground state and no chemical reaction could occur. But bosons can be in the same state, and they are important for superconductivity, because when the two electrons go into a copper pair, they are still fermions, but they act together as a boson. That means that all copper pairs come together into the lowest energy level. They will all be in the same state because they are boson now, and not fermions anymore. Now they can behave as one big group of particles in the same state. Because the copper pairs are bounded over a big distance, more copper pairs become overlap. This is a big overlap becomes engaged and now behaves as a large network of interaction. This network of interaction will attract to the batteries and therefore conduct. The colligative behavior of all electrons in the network and in the solid prevent any further collision with the lattice if any were to collide with an atom in the network can just recombine into new copper pair. To have the resistance, the whole network would have to collide with the lattice, and that's just uncertain to happen. So there is none.
There are two types of superconductor, type 1 superconductor and type 2 superconductor. Type 1 superconductor have a low critical temperature in a range of 0 Kelvin to 10 Kelvin. Type 2 superconductor have a high critical temperature greater than 10 Kelvin. Type 1 superconductor have a low critical magnetic field less than 1 Tesla, but type 2 superconductor have greater than 1 Tesla. Type 1 superconductor obey the Manar effect, which I will examine later, and the magnetic field can't penetrate inside the material. But type 2 superconductor obey the Manar effect, but not completely, as the magnetic field can penetrate inside the material. Type 1 superconductor have a single critical magnetic field, but type 2 have two critical magnetic field. Type 1 can easily lose a superconducting state by low intensity magnetic field. Superconductor type 1 are also known as soft superconductor. But type 2 superconductor is not easily to lose the superconducting state by external magnetic field, so type 2 superconductor are also known as hard superconductor. In type 1 superconductor, the transitions from a superconducting state to a normal state due to the external magnetic field is short. But in type 2, the transition from a superconducting state to a normal state due to external field is gradually but not short. At lower critical magnetic field, type 2 superconductor start losing its superconductivity. At upper critical magnetic field, type 2 superconductor completely loses its superconductivity. As here, this is the lower critical magnetic field. Here is they lose the superconductivity gradually. Here, it loses its superconductivity all. The state between lower critical magnetic field and upper magnetic field is known as intermediate state or mixed state. As a type 1 superconductor have a low critical magnetic field, so it can't be used in the production of a strong magnetic field. And a type 2 superconductor, it have a high critical magnetic field, so it can be used in a production of strong magnetic field. Now with the Meissner effect. Meissner effect can happen when the applied field doesn't exceed the critical value and the temperature are fixed of the superconductor. Under these conditions, superconductors exclude the magnetic field from their interior. When the temperature is greater than the critical temperature, the magnetic field passes through the magnet easily. But when the temperature is less than the critical temperature, the magnetic field can't pass through the magnet. So shown here, when the magnetic field doesn't go through the magnet, the magnet can fly a little bit. There are some application of superconductivity, which is a sensitive magnetometer based on SQUIDS, which is a superconducting quantum interference devices. Second is the fast digital circuits, and third is the powerful superconducting electromagnetic used in magnetic resonant imaging, or nuclear magnetic resonance, or something like this, or fusions, and also used in a low loss power cables as